Hello everyone. My name is Maria, and I'm going to give 3 lectures in this school regarding general relativity, the Hamiltonian formulation of general relativity, and numerical relativity. Why I think this is important to know, because it is a very let's say, very important topic nowadays, moreover with the advent of the detection of gravitational waves. So if you are interested in general relativity, then it's very important because it's kind of on the edge of research nowadays. And if your interests are more on particle physics, it's anyway good that you know this. You will be able to understand better what people are doing research today. So the schedule of my lectures is in this first lecture, I'm going to introduce the procedure, Dirac procedure for Hamiltonian systems. But first, I will give a motivation for all the topics for gravitational waves. Then, in the second lecture, we will take general relativity that you are studying in other lectures. And we will study like the general structure, the theoretical structure of general relativity, based on the Arnouit-Dessel-Misner formulation, which is basically like some Hamiltonian formulation on which you somehow break this covariance that you are studying in general relativity. And then we need to specify time and separate time from space. And in this way, we will study the evolution of space in time. Yes, this is not so easy because, as you have seen here, general relativity is invariant, is under coordinate transformations. So every time we talk about time, we are talking about a coordinate choice. So there are infinite choices that we can make. So this coordinate invariance is some very difficult topic to treat. So that's why one goes to these formulations. And also, this is the base, this formulation is the base for numerical relativity. So the first aim of this, I think my first aim was a bit too ambitious. It was to indeed put general relativity in some numerical code and solve Einstein equations. But I think, like after meditating a little bit, it was too ambitious. But I will be happy that you understand the main concepts that lead to these simulations of general relativity. And here you will be able to, after the course, you will be able to click here. These are clickable links with all the references that I will be using during these lectures. And in particular, here you will find some nice introduction to constrained Hamiltonian systems. Here the ADM, or 3+1 formalism of general relativity. You will find it here, here, and here. And this book is a very complete compendium of numerical relativity and what is the state of this field of research nowadays, although it is from 2010. It has like the theoretical basis for a lot of things that are used today. And I think a good motivation for studying numerical relativity is the detection of gravitational waves. So how are gravitational waves detected? Well, gravitational waves are a prediction of general relativity. It comes from solving Einstein equations in vacuum with very small perturbations. So probably this solution of Einstein's equations you will see in your lectures of general relativity. And also, here I am mixing 2 concepts that are consequences of general relativity. One of them is gravitational waves, and the other is black holes. Black holes are also a prediction of general relativity. You have Einstein equations, you solve them for spherical symmetry, and then you find this solution of black holes. So this solution of Einstein equations have been known since the theory was formulated 100 years ago, but in particular things like black holes and gravitational waves, Einstein himself did not believe that they existed. So somehow his theory was more powerful than him. It was telling him that this prediction, for instance, black holes, that light enter and cannot escape. It was something that it was not, they were not able to be conceived, this kind of objects. So they don't believe they existed. But they have been, like nowadays, they have been, we have found evidence for, in particular, like observing a black hole. We have observed black hole through images of a magnetic disk around a black hole. But what we have more evidence is a merger of black holes. Like observing just a black hole is a bit difficult, but usually these objects they are rotating around each other. So when they rotate, you know, when they have an orbit along each other, they emit gravitational waves, and at some point they just merge. Yeah, and when they merge, this is a very energetic process. So it emits a lot of energy. Therefore, it was one of the first things that it was detected on only 7 years ago. It was detected this merger of a binary black hole system, and it just started a new era, because now we are not only able to observe the universe with electromagnetic waves, with infrared, with ultraviolet, but also we can observe it with a totally new, different, let's say, telescope, which is a telescope of gravitational waves. So this detection was possible thanks to joint effort of both theoreticians and experimental physicists, because the detectors that were used, LIGO detector, it was two detectors, like two detectors on opposite sides of the United States, and they need a very precise, a very explicit precision in these measurements, because gravitational waves, although they are very powerful, they are very distant. So what you receive is some just even less than millimetric, something very small, let's say, perturbation on your detector, which you detect through interferometry. Yeah. But also, you don't only need to detect this, you also need to know what you want to see. Yeah? And what you want to see is some, let's say, phases of this binary black hole merger, and these phases, they have a very complicated pattern, you could say, and you have to predict this pattern, yeah, with very much accuracy, and you have to give to these detections, to these measurements, you need to give a lot of different possible mergers with different masses of black holes, for instance. And even if we don't believe that general relativity is our theory of gravity, if we believe that we have something else, then you will have to produce this kind of predictions with even another different theories that go beyond general relativity. So, however, and in order to motivate you, in 10 years more, we will have gravitational wave detectors in space. Right now, all our detectors are on Earth, but very soon we will have this LISA collaboration from, let's say, the West, but also we have Desigo detector from Japan, and 2 gravitational wave detectors from China. Yeah, and this is a very nice review that you can click it on it, from where I took this diagram. So these detectors will be in space, and they will have much better accuracy than the ones on Earth. So we will have lots of data, and we will be able to test very well general relativity, and hopefully to find physics beyond general relativity. So now my motivation for, this is a, okay, I cannot click it. Okay, you will be able to watch it later. But, well, this was some video on how, let's say, binary system of black holes, it generates some ripples on the curvature of space-time, and when they are in the phase of, in spiral, this spiral is just the 2 black holes are very distant from each other, but since if gravity works only with Newtonian gravity, let's say, this system will just rotate along each other, it will not collapse. But since this system is emitting gravitational waves, it's losing energy. So each time they rotate, they lose energy, so they come closer to each other. And at some point, this let's say weak gravity becomes very strong, and then we have like very strong ripples on the curvature, and they just merge in one black hole. Yeah, and after this merge, this final black hole, it has some vibration, which is like called the ring down, and that's what called quasi-normal modes of black hole, and you can also predict this. Yeah. So here is all the stages of this merger. This is what the spiral that I was telling you. So due to the emission of gravitational waves, it comes closer. Then you have like a merger, and here in this merger is when we need numerical relativity. For all the other phases, there are some, let's say, analytic physics that you can predict these phases. But for this phase of the merger, the gravity is just too strong. You cannot trust linear perturbations, which is like the typical gravitational wave that you study in general relativity. Yeah. So here we don't have small perturbations, and we need to solve Einstein equations exactly, let's say numerically. Yeah. So yeah, we need we need, in order to interpret let's say the measurements from observations, we need like waveform templates like the one that I show you here. This is precisely what it was detected in 2015. It has been detected like, I think, more than 40 other events, like black hole mergers and neutron with black hole merger, neutron star with black hole merger. But it's really important to know how to produce these templates. Yeah. And that's why one goes for numerical techniques. Even for the phases that we don't know, we know how to compute analytically, we still need to corroborate them with numerical relativity. Yeah? And the agreement is very good, except in this phase of the merger. And this is a very young field of research, so even like you might think that Einstein field equations are very well understood because they are from 1,000 years ago, but still, even in numerical relativity, there are these numerical techniques, you have totally different approaches, because it depends on which, what is the phenomena you want to predict. Yeah? What is the physical, let's say, symmetries of your system? For instance, it's not the same that you have two black holes rotating in a, let's say, in a tilted plane, than two black holes just colliding in a, let's say, in a line. That's totally different symmetries, and you have some, let's say, it's more easy to solve when the system has, it's just in one line, in one line. You can even almost solve it analytically. But in order to understand the theoretical aspects of this, we will study this ADM formulation. But for this, we will study Hamiltonian mechanics, which I think it will be a bit easy because my colleagues, they have already been telling you the use of the Hamiltonian, for instance, in quantum physics is very, let's say, very important. And for us, like theoreticians, that what I really do is not numerics, but it's a more theoretical aspect. So the Hamiltonian approach, it allows us to, for instance, go beyond general relativity and try to check what are the degrees of freedom of these modified gravities, and it allows us to check which modifications to general relativity are, let's say, well behaved, and which other ones we should just get rid of. For this, the Hamiltonian formulation is a very powerful tool for just considering extensions to general relativity, or just forget about them. Yeah? I will present the Lagrangian and the Hamiltonian formulation in terms of, let's say, some mechanical system, not in field theory, but the extension to field theory is it's not so difficult to do once you understand the concepts. So I will start first, I think you already know more or less what a Lagrangian is. So Lagrangian is some, let's say, generalization of any mechanical system, any physical system that you want to describe. Is governed by equations of motion. And these equations of motion, you can obtain them from a Lagrangian that forms part of an action, and then there is a variational principle that allows you, that is like some postulate in physics. It's a postulate that it works very well with all our theories. So we make the postulate that there is this concept of the action of a theory written in terms of the Lagrangian. The Lagrangian depends on, describes the movement of a point, let's say, in space. You determine the position of this point with these coordinates. You can have like n points that you want to describe with these coordinates, and also these points, you don't only specify the position but also the velocity that it has. And then you write the Lagrangian in terms of the coordinates and the velocities for n, let's say, particles. And as you also saw in general relativity, why don't we write, for instance, here it's a first order time derivative. Why don't we write second order time derivative? Why? Because we want equations of motion of second order. So if I add a double time derivative, then I get fourth order equations of motion. And we already know, like from, let's say, before the beginning of the 1900s, that fourth order equations of motion are not very good for working because it describes some sort of unstable systems where it appears like ghosts, which are called like Ostrogatsky ghosts. So in the most general case, fourth order equations of motion are not very stable. So that's why we choose to describe the real world with second order equations of motion. Precisely from this kind of Lagrangian, we obtain equations that are second order in time, and then if we expand Lagrange equations in greater detail, we find like indeed equations of motion are second order in time, and this object that goes with this time derivative of the velocity, it is called the Hessian system, and it contains the kinematics of a system. Yeah, it's very important, and it is in any, let's say, theory that does not have constraints. This is an invertible matrix. Yeah, and then this is where it finishes my Lagrangian formulation, because now I can just go to the Hamiltonian picture. So in the Lagrangian picture, you work with the position and the velocity. Now we'll see that in the Hamiltonian picture, it is better to work with the Legendre transform of the velocity, and then this velocity, we can express it in terms of these momenta, the canonical momenta. The canonical momenta, it depends on the position but also on the velocities, and somehow we are transferring the kinematics of the velocity to the momenta, yeah, through a Legendre transform of the Lagrangian. And these momentas, they can be expressed in terms of the velocities if this Hessian is invertible. So if the Hessian is invertible, it's an invertible matrix, then all the momentas can be solved as a function of the velocities. If not, then we are in presence of a physical system with constraints. Usually in physics, like almost all let's say the physical theories that represent real physical phenomena, they have constraints usually. In some cases they are very easy, like in electromagnetism, for instance. In general relativity, it's a bit more complicated. So we will see all the constraints associated with invariance under change of coordinates. And so if we cannot invert the Hessian, then we will have some null eigenvectors of this matrix that they will give us relations between the velocities and the positions, or the positions and the momentas in the Hamiltonian picture, and this, at least in the Lagrangian picture, they are called primary Lagrangian constraints, and in the Hamiltonian picture they will just be called primary constraints. So yeah, here is where in the Hamiltonian picture, these primary constraints there are relations between the momenta and the positions. Yeah? And then a mathematical object that is defined in Hamiltonian mechanics, and you have seen already in quantum mechanics, is the antisymmetric commutator. So this commutator, Ale was expressing it with square brackets. I will express them in like this mechanical, in classical mechanics. I will express them with these brackets. So it is the anticommutator. I take two functions that depend on the position and the momenta. I compute this commutator, and this object, it has some, let's say, it has some deep mathematical meaning that I would not like to talk about here. But let's just take the definition, and then let's take that in the previous slide I found a set of primary constraints for a particular theory. This is like very general. For any theory, you will have primary constraints. You define this boson bracket, and then somehow in the phase space of the theory, the phase space, once you go to the Hamiltonian picture, it is expressed by a set of momentas and velocities. So for a very specific coordinates, yeah. So these coordinates, let's say for a very simple system, you can have just one momenta and one position. Then a constraint in this very simple system is just a relation between the P and the Q's. And this somehow we call like a hypersurface. So the concept of hypersurface we will see later also. But usually if I have a plane, I have two coordinates. This is like a plane, a space. And a hypersurface in a plane is a line, yeah? An object, mathematical object that has one less dimension. Yeah? So in particular you can like increase the number of coordinates, and then instead of 2 axes you will have 4 axes, and instead of this you will have like some plane in this axis. That's how you imagine like hypersurface, reducing the say the dimension. So this is very abstract, but primary constraints, if you have n primary constraints here, sorry, p primary constraints, then you will have a hypersurface gamma p. Yeah? And then we will assume that this Hessian, the rank of the Hessian is, well, the matrix, when you have constraint, is not invertible, but if we assume that the rank of this matrix is constant throughout all this phase space, this is the phase space, the full phase space, not the hypersurface. So you will define this like a surface of primary constraints, and you will assume that the primary constraints, they are satisfied in this hypersurface. Yeah. So I will say that, for instance, if you have a function in the phase space, and I can write it as a combination of primary constraints, then it will be weakly zero in the hypersurface, because in this hypersurface I have my primary constraints that are satisfied there. Yeah. So this object, weakly zero, we will use also later. So now this is like the definition of the canonical Hamiltonian that you have also seen in your lectures of quantum field theory and quantum mechanics. And even when I defining here the velocity, I'm defining the Hamiltonian in terms of the velocity, the momenta, and the Lagrangian that also depends on the velocity. You can prove through variations, some very simple computation, you can prove that this Hamiltonian depends only on the positions and the momentas, yeah, on the coordinates and the momenta. So since these primary constraints that I defined previously, these primary constraints, they are weakly zero in the hypersurface. So you can also prove that the predictions of the theory, they remain invariant if I change this Hamiltonian by a combination, a linear combination of primary constraints, where these are arbitrary functions of the position and the moment. Yeah? And then the time evolution, if I take this Hamiltonian, I can also prove that if I compute the time derivative of a function, I can write this time derivative here in terms of my Poisson bracket that I defined previously. So any time variation of any function in the phase space, it can be written like the commutator of the Hamiltonian. Although the Hamiltonian here had two parts, like the canonical Hamiltonian here and the extra term that has primary constraints. So finally, any function I can express like a Poisson bracket between the canonical Hamiltonian and the primary constraints. So, I can, for a physical theory to be consistent, I need that the primary constraints, these primary constraints, they are preserved in time. So this is true for any theory. Yeah, any theory that has primary constraints, it must have the primary constraint preserved in time. Otherwise, they are not constraints. Yeah, they have to be preserved on all the time evolution. And then I will demand that for any physical theory that I have, all the primary constraints will be satisfied. They will be preserved in time. So I impose that the primary constraints have this expression is 0. Yeah, and then this impose some conditions on these three parameters that I define. And I'm changing a bit the notation here. This 0, I later call them like euro. Yeah, these are three functions depending on the momenta and the coordinates, and I need that this equation is satisfied. Oh no, I'm imposing that this equation is 0. So this matrix is not the Hessian matrix that I showed you before. Is this matrix that is formed between the primary constraints and it's a matrix formed by Poisson brackets between primary constraints. And then this equation, I have 4 options for solving this equation. So sometimes the solution of this equation will be simple because it will be trivially satisfied. For instance, let's see which cases. So in this case, for instance, where neither these are weakly 0, it means that I can determine these Lagrange multipliers. I can fully determine them since this matrix will be invertible. In another case, I will find these Lagrange multipliers. They will be 0. If they're weakly 0, then the equation will be satisfied. In other cases, there is only a particular number of Lagrange multipliers that I can determine, but in this case, I need to put new conditions for this equation to be satisfied. And these new conditions are secondary constraints. And then later, I need to impose that these secondary constraints are also preserved in time, and then they give me rise to a new set of equations. I have to put them here in this matrix, and then I will get a new C, a new H, and I have to do all the process again. And this is what is called an algorithm, the Dirac algorithm. So I can apply this Dirac algorithm to any theory, any physical theory that you give to me, and you can prove that your theory is consistent if you don't get any more. After you finish all this procedure, you don't get new constraints. Yeah. So at some point, this Dirac algorithm is kind of is old, as you can check because it's from Dirac. Yeah. And however, it's very powerful in order to just check the theoretical consistency of any physical theory. And then we can say that we will have a set of, let's say, primary constraints that we just found from the equations of motion. We did not find them from the equations of motion. We just found them from the definition of the momentas. And we will have another set of secondary, tertiary constraints, which are used in the equations of motion. But in physical theories, there is another more useful classification of these constraints, which is first and second class. And for doing this, we will redefine aural constraints in first and second class. And for this, we need to use our Poisson bracket that we defined previously. So the functions that are first class, they will satisfy that the Poisson brackets between all these constraints, they are weakly zero. They just give you weakly zero, they just give you the constraints, another constraint that is zero. And if the constraints are not first class, are second class. Yeah? And then we make some redefinition, we make two groups of constraints, first class and second class. Yeah? And for the second class constraints, you have to, they will form a matrix of Poisson brackets, which is not, it is always invertible. If it is not invertible, then you have first class constraints there. So the importance of this classification in first class and second class is that first class constraints, they have some physical meaning, very deep physical meaning. They produce gauge transformations. So you already know, probably know about the concept of gauge transformation. We will see very soon an example of electromagnetism, but gauge transformations, for instance, in general relativity is the change under coordinate transformations. Diffeomorphism invariance is a sort of gauge transformation. And if you apply this procedure to general relativity, you will find a set of first-class constraints, and these first-class constraints, they generate diffeomorphism transformations on the metric. Yes? So you can count the physical degrees of freedom of any theory by counting the number of canonical variables, which they come in pairs because you have one momenta and one q, and if you have like n particles, you have n times 2 is number of canonical variables, and then you can count which are the degrees of freedom that your theory has by to this number, removing the number of second class constraints, and then removing 2 times first class constraints. Yeah? And now we will use this formula and all this procedure for a very simple theory, electromagnetism. So you have already seen this. I think you're already familiar with this action. Yeah, this is the strength field for electromagnetism, and you define this strength field in terms of a potential mu, and this is precisely like let's say the degree. The vector that you associate with the electromagnetic field and the magnetic field. Yeah. Sorry, with the electric field and the magnetic field. Yeah. And yeah, you define this Faraday tensor, and then you apply Dirac's procedure to this theory. You define the canonical momenta conjugated to your coordinates. So your coordinates are the electric and the magnetic potential, and the canonical momenta are the variation of the Lagrangian with respect to the time derivative of this coordinate. Yeah? And then you obtain the 0 mu component of this tensor. And since this tensor is antisymmetric in these indices, you see that if you replace mu by 0, then this will be 0, because I'm just repeating these two indices. So if I repeat the indices, since this tensor is antisymmetric, you get 0. So you see here that just from the definition of this momenta, you obtain a constraint, a primary constraint. Yes? I didn't use any equations of motion here. I just used the definition of the momenta. So this is a primary constraint for electromagnetism. And now I should make the difference that all the procedures that I showed you before, I defined like for classical fields. Yeah, sorry, for classical mechanics. Like it's just some position of some. This is like the position of a particle. It's like the coordinates. In field theory, I have some, let's say, physical field that depends on the coordinates. That means, like, if I am here in this point in space-time, I have a value of my field here, and then I change my position, and I have another value. That value of the field is expressed by this function. So this value, it changes from point to point. And then it means that if I have this primary constraint, it counts as 1, but it represents an infinite number of constraints, because in each point in space, I will have this satisfied. So here, I will have that pi 0 is 0. If I am in this coordinate, I will have that pi 0 is 0, and so on, in all space. So in principle, it's like an infinite number of constraints, but I will count them as just 1. Yeah? And then I will build, since I already have here you have the velocities here, because the f0, it contains a time derivative there. So this is somehow, it represents like the velocities here, and the velocities are written in terms of the momenta. Therefore, I can solve for the velocities in terms of the momenta, and I can rewrite the Lagrangian density in terms of the momenta and in terms of this spatial part of the f mu nu. Yeah. Here, these indices I, they represent space coordinates, and the mu equals 0 represents time. Yeah, so here I only have spatial derivatives which do not encode any dynamics in time. Yeah, they are just spatial derivatives. And here I have like the kinetic term. Therefore, I write the Hamiltonian density. As I showed you before, it was pi times velocity minus the Lagrangian. So here is the canonical Hamiltonian. And as I also show you here are the velocities, but here I write explicitly. The velocities, indeed, can be written in terms of the momenta and on something that does not have any velocity. Yeah? And here I can solve them, because basically I can solve all the velocities, because in electromagnetism the only primary constraint is this one. Yeah? And then I remove it from the definition, and I can solve all the velocities. And I can write the canonical Hamiltonian, and here, this is not the result that you will obtain by solving and replacing here, because I did two things. I integrated by parts, and I threw away a boundary term. Which one? Precisely, well, there is a term that appears with spatial derivatives of the A0. So this is spatial derivative. I just pass it to the momenta. Yeah. So finally, you get that the spatial derivatives are applied in the pi. Yeah. So this is the canonical Hamiltonian for electromagnetism, and then I can add the primary constraints that I found. I told you before that if I add primary constraints to the Hamiltonian, the dynamic does not change. In principle, you cannot consider them, but I think it's better to consider them. So when you consider them, then you write the primary Hamiltonian, and you can define the fundamental set of Poisson brackets, as you have seen in, for instance, the free scalar field. You have defined fundamental Poisson brackets for the operators. Here I am defining the fundamental Poisson brackets for the fields. Yeah, and these Poisson brackets, they are different from 0 only when these coefficients are the same. Yeah, are the same. Let's say the same coordinates. And then I will impose that the primary constraints are preserved in time, which is equivalent to compute the Poisson bracket of the primary constraint that I already obtained, the only primary constraint of electromagnetism, and the primary Hamiltonian. And this computation, it gives you, different from 0, yeah? It gives you the divergence of the momenta, but in order to make this procedure consistent, I will impose that this divergence is 0. Therefore, I obtain a secondary constraint in electromagnetism. Yeah? And now I need to impose that this constraint is preserved also in time. So I will compute the Poisson bracket of this divergence with, again, the primary Hamiltonian. And I obtain that this is exactly 0. So here in electromagnetism, I just finished the Dirac procedure, the Dirac algorithm, and there are no more constraints. The only constraints of electromagnetism are the primary constraint here and the divergence of the pi, which is a secondary constraint. And that's it. And indeed, if you work electromagnetism in the Lagrangian formulation, you will find this as the equations of motion or electromagnetism. Yeah? Yeah?
Why is the derivative of the momenta is not exactly zero?
This, why it's not exactly zero?
Yeah.
What I mean is that I obtain in the Hamiltonian formulation, I obtain this as a requirement that I have to impose to my, let's say, to my momentas. When I first took the theory, I did not have any restriction over this pi here. When I started, I did not put any restrictions. I just let the algorithm tell me which are the equations of motion. Yeah? And when I do all the procedure, then I indeed get that this has to be zero. And why I call it weakly zero? Because this is a constraint. Like, first, I didn't have any restriction between the pi and the a nu. Here, like in electromagnetism, the phase space changes to pi nu and a nu.
Maybe you should just say it explicitly. What you mean here is not approximate.
Yes, this is exactly zero after I do all the procedure. Yeah, but this is like some technical thing that one defines in this Hamiltonian mechanics. Like, I obtain that this is zero. But yeah.
One is on a constraint surface.
Yes.
I define that. It's not about approximation.
Yeah, it's not approximation. It's a definition I did here. This weakly zero in the constraint surface. But indeed, it is zero for technical purposes. Yeah, thank you for the question. So yeah. So now, what as I told you, in physical theories, it's better to talk about first class and second class. And then, if I apply, let's say, Dirac algorithm to this theory, I will compute the Poisson bracket between this primary constraint and this secondary constraint, and I get zero. Yeah, it means that both of these, these four constraints, they are first class, and they produce gauge transformations on electromagnetism, which I'm not showing them here, but I can show later if you want. But then I count the number of degrees of freedom in electromagnetism, and I apply the formula that I showed you before, and then I have four pairs of canonical variables, because for each coordinate I have one pair. So for mu equals 0 is one pair, for mu equals 1, second pair, 2 and 3, and then I have four pairs. It means 8 variables. I remove two first class constraints, and I obtain 2 degrees of freedom, which correspond to the two polarizations of the electromagnetic field. Yeah, this is like already it is known, and it turns out, and of course it's a totally different theory, but in general relativity I also have 2 degrees of freedom. Yeah, and these are the polarizations of gravitational waves. In electromagnetism, these are polarizations of electromagnetic field. Yeah, not because the theories have the same number of degrees of freedom means they represent the same. No, they are totally different phenomena. However, the Dirac algorithm allows you to find like the true number of degrees of freedom. And all the other variables, additional variables that you get, they are, let's say, something that you can fix. You know? And now, yeah, I have a little bit of time, fortunately, but I think not too much because I have to finish like in 10 minutes. Yeah. I think I have a little bit of time to introduce what is going to be the next lecture. We will do all this procedure, Hamiltonian procedure, for general relativity. And when we do it, we will find the first class constraint for general relativity associated with diffeomorphism invariance. But you can also find the number of degrees of freedom in general relativity through linear perturbations. And this linear approximation is true when you have very weak perturbations of the gravitational field. In the examples that concern numerical relativity, these perturbations are very strong, so you cannot trust linear theory, and that's why we have to go to the nonlinear to study the full nonlinear behavior. But I think, yes, I put here like how do you linearize Einstein equations. I'm just showing you very schematically. I think you will study more that in the general relativity lectures. But the main idea is that I would like to study the space-time, how the space-time behaves in vacuum with little perturbations. So these little perturbations, I have to perform these little perturbations around Minkowski background. You can also perform perturbations around other backgrounds. For instance, if you have cosmology, cosmology is expressed like by an expanding universe through a scale factor. So here, instead of having Minkowski background, you will have the Friedmann-Robson-Walker space-time expanding, which is also a solution of Einstein's equations. And then you will get a theory for cosmological perturbations, which I think you will also see. For instance, if you have a black hole, you can also perturb, make small perturbations around a black hole. And this is precisely the final state of the merger of two black holes. You can also study perturbations around this black hole, but here you need to put the solution for a black hole, which is Schwarzschild space-time is the solution for a black hole that is, let's say, does not rotate, yeah, only has mass. But gravitational waves appear from perturbations around Minkowski space-time. And then you already saw the shape for the Einstein tensor in the previous lecture, and this is it's not very difficult. You just take your metric, take this small perturbation, and then you compute the Einstein tensor. You know, you compute the Levi-Civita tensor and the derivatives, and then what you do in this linearization of equations is you take every time you get something. For instance, h mu square or to the third power or etc. You just neglect these terms. Since this is a very little perturbation, you will just keep the things that are linear in this h. And precisely this Einstein tensor is what you obtain by replacing this in the formula for the Einstein tensor. And you can see that all the contributions here, they only have one h. It is linear in h. Here you have double derivative of h, double derivative of h, the trace of h, the, let's say, double covariant derivative of the h, and here you have the Minkowski metric and another h and another h. This is linear in h. And then these little perturbations, you will make a decomposition because you want to study which are the modes that they really propagate through this equation. And you will make this decomposition, you will replace this decomposition in the Einstein tensor, and as you saw, like this Einstein tensor, you just equate it to matter, yeah? And then if you replace this in the Einstein tensor, you also have to decompose the energy momentum tensor in its components here, 0, 0 component, 0, j component, and ij component. And you can study these equations for the linear perturbations, and then you will find not all the functions that you define in the decomposition, they will have propagation. The only ones that have propagation are these tensor perturbations. All the other ones that you consider, these are like scalar perturbation, vector perturbation, another scalar perturbation, you find that they don't have any dynamics from here. Yeah? This is a Laplacian, but in space, not in time. So this does not propagate. It doesn't have any dynamics. You can solve it in terms of the matter content and the spatial derivatives of these tensor perturbations. And then, also from this 0j equation, Einstein equation, you also get that here you don't get any time derivative for the psi. Yeah. Also don't get any time derivative for the vector perturbation, so this vector perturbation has no time derivatives, therefore can be determined, and it's not a dynamical degree of freedom. And here you indeed get some time derivative for the tensorial perturbations, and these are precisely the ones that are used to describe gravitational waves. But I told you that general relativity has only 2 degrees of freedom. And here I have at least 6, yeah? So not all these degrees of freedom are propagated, yeah? So for that, I think you will see that later in the lectures of general relativity. But at least you see that the time derivatives are only in this object. And this is where gravitational waves are encoded. Yeah? But I think for now I don't have time for explaining it. And I think I will have to explain the... my idea was to show you that in the linearized Einstein equations you can find the degrees of freedom. But to make the, let's say, correct counting and non-ambiguous counting, we will have to go to the Hamiltonian formulation. And for that, I need to define some mathematical framework for it, where we will see the concepts of induced metric, explicit curvature, and the time evolution of these objects, which will finally give you the dynamics of general relativity. But for that, I will need some, I think we will see in the next lecture. So yeah, I think it will be, for now, that will be everything. And if you have any questions, you can ask. Or write to my email, or we can talk tomorrow. Yep. So.
Yes, that's it for today.